What we're going to talk about today is a revolution in interventional medicine. We're going to change how medicine sees, learns, and predicts based on data coming from inside the body, the true point of care. The challenge we're solving is that critical procedures today are complex. They're done from outside of the body, from a remote distance, trying to be very precise inside the body. You need to hit a small target and avoid critical structures. This requires complex hand-eye coordination and a high cognitive burden. It takes a lot of skill to do these procedures, and there's not enough skilled practitioners out there, so their patients aren't being served. The key is visualization. Seeing the instrument is very difficult. There's either limited real time, CT is only snapshots in time, or ultrasound is very difficult to see the instrument and has bad tracking. In total, the tools today are inadequate for the challenge. And this is where needle view comes in. It starts with the location, because it's all about the location. What we've done is we've made it very easy to know exactly where you are. This is an image, an ultrasound image of a needle being inserted. It's an echogenic needle made to show up in ultrasound. It's very difficult to see. It's actually on the right-hand side. Those skilled in the audience probably can see it, but for most it's difficult. What we've done is we've made it trivial to know exactly where the tip of the instrument is. What you're seeing here is simple but powerful. It's an indicator, a dot, where the instrument is. Now, ultrasound is a 2D modality. There's only a plane shown. What you're seeing here is the clinician sweeping an imaging transducer in and out of the plane of the instrument. And so you're seeing a bar that grows or shrinks depending on how close you are to the point of the instrument. And what makes this all possible is an astounding sensor. It's a sensor that's microscopic in size, so it will fit on nearly any instrument out there. It's not electrical, so the signal's not degraded by electromagnetic interference. It operates in heat and cold, for example, ablation environments. It's self-calibrating. There's no external apparatus needed, no setup, no calibration. You just walk up, use it, it works. And it's all in a low-cost, disposable architecture. It breaks down barriers that clinicians have had to deal with. Before in an ablation cloud, it'd be hard to see a needle. In contrast, the needle disappears with the brightness of the contrast media. Needle view sees it. Deep inside the body, even in shadows, behind ribs, behind devices, we have no problem. We show the clinician where it is. It works at any angle and at any depth with any workflow. So it's across the spectrum of application and body parts. This alone is incredible, but there's more. The sensor that we've developed is so powerful, it'll pick up the acoustic energy from an ultrasound transducer locally and reconstruct an image from the tip of the instrument. And we've added temperature sensing. We can monitor the temperature to within fractions of a degree. Great for monitoring ablations and assessing the treatment. And we've added pressure sensing. What you have here is a sensorized catheter in the heart, and you're seeing the mechanics of the heart beating. In addition, you can get feedback on when you're hitting different organs or tissues. You can see when you're up against a membrane. You know when you've pierced it. You know when you exit it. Now, this is a forum for AI. I haven't talked a lot about it. This is incredible technology, but AI is where it levels it up. What I've just described is multi-modality sensing, and that results in a rich multimodal data set. And AI is great at taking lots of data and making it insightful and informative. So if you combine location, imaging, temperature, pressure, you basically start to develop a fingerprint of what is being seen, a fingerprint of the tissue. And with that, it offers a potential for tissue characterization, tissue differentiation, tissue recognition. Now, I've talked a lot about a procedure at the present, but what about procedures worldwide and procedures in the future? Right now, most procedures are done, and then the learnings from it are summarized by a clinician after the fact. So many details are lost. With Needle View, you are now recording a procedure with a rich data set linked distinctly to the point where the action is happening, and it's recording the whole procedure from start to finish, from entry to exit. Compile this, aggregate this, and you can start to see how all these learnings can help to surface the best procedures and inform against potential complications. Every procedure, every needle view procedure becomes a step towards improving medicine. And let's talk about the evolution of where we are, the trajectory we're headed. Now procedures are done manually, going towards computer-assisted, semi-autonomous, and robotic, but these machines need to be trained. Where are they going to get the data? We've started capturing that data to help give us this future. I encourage everybody to visit us, booth 231, put your hands on the system, see it for yourself. We're always looking for partners and collaborators. Thank you.